Think about the following problem. Let the sequence be random variables such that each xn is from some probability space to the extended real line such that each xn is finite on this probability space almost surely. Or in other words, this means the probability of xn being finite is 1. And now here's the question. Does there exist constants c sub n going to infinity such that the probability of the limit of this quotient xn divided by c sub n equals 0 is 1. Namely, almost surely this c sub n could run much faster than x sub n. Do you think this is true? Given a sequence of random variables that are finite almost everywhere, can you always find constants whose growth rate could beat x sub n's eventually? And almost surely. The answer is yes. It is always possible to pick such constants, such sequence consisting of constants that beats your random variable when n goes to infinity. And the proof uses the Borel Cantelli lemma. So here's the proof. So how are we going to use the Borel Cantelli lemma? Again, I copied the statement of the Borel Cantelli lemma down in here. And you see, there's no independence at all in this problem. So we are going to use the first statement for the Borel Cantelli lemma. Remember, in another video, I talked about a very important corollary of the first statement of the Borel Cantelli lemma, which says the almost complete convergence implies the almost sure convergence. So recall that we proved in another video that if you have the almost sure convergence, namely for any epsilon greater than 0, the summation of xn minus x greater than epsilon's probability, where summation is from n equal to 1 to infinity, is finite. Then xn converges to x almost surely. And in our situation here, that this limit being 0 has property 1 corresponds to the almost sure convergence of this quotient to 0. So in this problem, this almost sure convergence corresponds to the almost sure convergence of xn by cn to 0. And this hypothesis should correspond to something like this. For any epsilon greater than 0, the summation of the absolute value of xn by cn greater than epsilon, taking the probability of this event and the summation, gives you a finite number. So now it suffices to construct our constant c sub n such that this guy is finite. So our goal will be to construct c sub n's such that for any epsilon greater than 0, this sum is finite. And keep in mind, our choice of c sub n is supposed to be independent of epsilon. However, it doesn't seem to be easy for us to choose c sub n that is independent of epsilon, because what we are supposed to do is to make each of the individual term very small, say less than or equal to 1 over n squared, so that the summation is finite. But somehow, you should have feeling that no matter how we choose c sub n, it always depends on epsilon in some way. To avoid this problem, we're going to use a very classical trick in analysis. We're going to replace epsilon by a variable that goes to 0. Say let's replace epsilon by 1 over n. So let's see. We're going to replace epsilon by 1 over n. And we consider this event. The event where this quotient, the absolute value, is greater than 1 over n. And we take the probability of this event and take the summation. And now, this summation being finite will actually imply that for any epsilon greater than 0, this summation is finite. Do you see why? We have this implication because for any epsilon greater than 0, there are only finite many n's such that 1 over n is bigger than epsilon. All but finitely many 1 over n's will be smaller than epsilon. So all but finitely many terms in here will be bigger than this, because 1 over n is smaller than epsilon. And we do not care about those finite terms. Those finite terms always sum up to be a finite number, because this is a probability measure anyway. So this is true. Okay, now do you see a way to construct c sub n such that this sum is finite? I'll let you think about it for a while. I think you should be able to find the solution, find a construction for c sub n. But let me tell you the answer anyway. So here's a construction of c sub n. The goal is to pick c sub n such that this guy is less than 1 over n squared. And this guy is actually equivalent to this. The probability of the absolute value of xn greater than c sub n divided by n is less than 1 over n squared. We're going to choose c sub n to be positive, so we can ignore the absolute value for c sub n. So why is it possible to choose c sub n such that the absolute value of x sub n is greater than this guy has a very small probability. Here, we're going to use the fact that x is finite almost everywhere. Because x is finite everywhere, the probability of the absolute value of xn being less than infinity is 1. Or in other words, the probability of this guy being equal to infinity is 0. So for each fixed n, the probability of this intersection, where m is from n to infinity, of the events xn is greater than m, is same as the probability of xn equal to infinity, which is 0. So they are equal because those two events are actually the same. If you pick omega from the probability space and xn for omega is greater than m for any m, then xn for m must be infinity. So those two events are the same and their probability are the same. And it follows from here that for each n, you'll be able to pick a capital N that depends only on n, such that the probability of the intersection of m from 1 to capital Nn of those events is less than 1 over n squared. However, let me copy the statement in here. What is this intersection? This intersection is nothing but the last member in this intersection, because this event as a set is decreasing with m. So this intersection is just the last guy. So you get the probability of this is less than 1 over n squared. Now we compare this with our goal. Our goal is to construct C sub n's such that this holds. Okay, now do you see how to choose C sub n's? It is simple. I'm just going to choose C sub n to be n times capital N sub n. This is our choice. Once this is chosen, then we realize our goal through this. And as a result, we will have each individual term of this guy is bounded by 1 over n squared. And that implies, by my earlier explanation, that this infinite sum is finite for any epsilon greater than 0. And that is the definition of the almost complete convergence, which implies, by the theorem I proved in another video, that xn converges to x almost surely. Now here, it means xn divided by C sub n converges to 0 almost surely. And that is the goal we want to prove for this problem. So this finishes the proof of this problem. That's the construction of C sub n. So what we did today is that we provide some mathematical explanation for this rule of life. In our life, we frequently see that being constant could always be better than being random. It will be easier for us to be successful if we work on something constantly, rather than make random choices. Specifically, so you may have many choices in your life. You might want to become a mathematician, or you might want to become a data scientist, or you may want to become a software development engineer, or you may want to become a quantitative analyst, or some other career plans for yourself. You don't know which one is better. For example, being a mathematician may give you a chance to become very famous. You might create a theorem, prove a conjecture that is named after yourself. You'll be famous for hundreds of years. And maybe become the other three will make you rich. You could accumulate millions of dollars in your life, running your own company, and retire early, say in your 30s. However, I want to emphasize here is that although there might be no best choice for you, it will be important that you be constant rather than be random. So what you do is that you try to make a good research about yourself and try to make it clear what career path is best for you. And you choose that particular path of your life and keep going. Then you'll be successful. I have seen people who made random choices. They want to be a mathematician at a point, maybe want to be a data scientist at a point, and want to be a quant at some point. But in the end, that person may not be very successful. If there are any life philosophy related to this problem, that's it.